Welcome back to my channel. In this video I will try to analyze the charging and power on circuit of the Nintendo Switch. In this presentation Nintendo Switch Lite is used as a main example, but this analysis can also be used for the OLED version, the version 1 and version 2 Nintendo Switches, because they use the same integrated circuits. Nintendo Switches use different integrated circuits like the BQ charging IC, the USB-C power delivery controller, the fuel gauge IC and also multiple power management ICs. I am going to explain how these ICs operate and how they are communicating with the APU to get a better understanding when you have to troubleshoot this circuit. Most of the time when you have a no power conditions, one of these ICs could be faulty. I am not a professional engineer, so there can be a mistake in my analysis because there are no schematics. I have analyzed datasheets, circuit traces and my own personal experience to make this video. If you find a mistake or you have more information about a specific topic, please add your comment in the comment section. To produce these types of videos takes a lot of time and research. If you like my content and if you would like to see more of these types of videos, please subscribe to my channel and help this channel grow. So let's start. The Nintendo Switch uses a USB-C port, it's also known as a receptacle. A USB-C receptacle refers to the physical connector on the Nintendo Switch that is designed to accept a USB Type-C cable. The USB-C receptacle is a small oval-shaped port that can be found on smartphones, laptops, tablets and other gadgets. USB-C has two USB 3.1 connections. So this is super speed lane 2 and this is super speed lane 1. And the speed goes up to 10 gigabytes per second. Commonly used for the DisplayPort or the HDMI signals. Then we have USB 2.0. That are these pins. So these are the differential pair for the data signals. And the speed is up to 480 megabytes per second. Then we have CC1 and CC2. CC1 and CC2 are for the power delivery functionality. So the CC1 is also known as a configuration channel 1, configuration channel 2. And these are communication signals that will communicate with the host, in this case the power supply, to negotiate which power the destination wants. So if Nintendo Switch wants 5 volt, it will ask for that, or 5 or 10 or 15 volts. It depends on what the power supply can deliver. The pins in yellow and in the red are the power delivery functionality. So the requested voltage will be sent through these V-bus pins. It can have up to 20 volt, but for the Nintendo Switch it can go from 5, 9 till 15 volts. Also a key feature of the USB-C port is its reversible design. So the connector can be plugged in either way, making it convenient for users. So we don't have to look at the orientation of the cable, but we just can plug it in. And the cable will make contact to one of those rows. So if you look at the first pins, when you rotate the cable, those pins are mirrored on the bottom side. The USB cable has most of the time only one row of connections. Also, a CC2 connection is possible, so it can have one row of all the connections and also a connection to the CC2. In some cables, there is an integrated circuit in the connector and that needs power. So let's say CC1 is used for communication, then a CC2 will become VCon. So it depends on the orientation of the cable. In the other case, if CC2 is the configuration channel or the communications channel for the power delivery, then the CC1 will be configured to deliver the VCon power rail, and this power rail will be used for the integrated circuit that is implemented in the USB cable. Then we have the secondary bus, also known as the sideband use. So this is the sideband use 1. This is sideband use 2. So the SBU pins are used for sideband signaling, which means they can carry auxiliary or additional signals that are not part of the primary USB data or power transmission. So these signals can be used for different purposes. One purpose would be like sending the audio signal back to your headphones, and that can use the sideband use channel. So this is the receptacle. So this will be a port on your Nintendo Switch device. The CC1 and CC2 are used in the discovery, configuration and management of connection across the USB Type-C cable. So when you plug in your USB-C cable, the CC pins are used for communication between the devices to negotiate the power delivery and other capabilities. In the plug, so in the cable, you can see there's only one communication pin, and this is connected to the cable to establish signal orientation. So this will determine in which orientation the cable is plugged in into this receptacle. And because this is the communication pin, the other CC2 will become VCon. And the VCon is used as a power rail for powering the electronics, so the integrated circuits that are in this plug. Also, there is one differential data pairs implemented for the USB 2.0, and the other one will be blank. So let's say the source is the power supply that will deliver the power to the Nintendo Switch, and the Nintendo Switch is the device or the sink. In the first case, we don't have a cable connected, so the V-bus is not powered, so this is a cold socket. And the Nintendo Switch Lite will pull the CC1 and the CC2 line, so it will start checking if there is communication on the CC1 or the CC2 lines. So let's assume that the source, that one of the CC lines is connected to a power supply with a pull-up resistor. When the signal goes to ground, there is a signal present on the line. That is how the detection works. Because the device is pulling the CC1 and CC2 lines, when it detects, so let's say CC1 is the communication line, when it detects the communication on the CC1 line, for example, the CC2 will be configured as a VCon channel. So VCon will become a power rail to power this IC in the connector. So this cable needs VCon to operate because this IC needs power. So that will be delivered to the VCon channel. Default, the V-bus voltage will be 5 volt, and then the power supply will send messages to the device, the Nintendo Switch Lite, saying I can deliver 5 volt at 1 amp, 9 volt at 2 amps, maybe 15 volts at 3 amps, and the device will respond, I want 15 volts. The host will send a message back saying I will deliver 15 volts, and after this message is sent, it will start raising the voltage on the V-bus line. When the voltage reach 15 volt, it will send a message, I'm done. That is basically what the power delivery IC does. Here you can see a Nintendo Switch Lite mainboard. So this is the USB-C port section. So this is also called a receptacle. In red, all those pads are test points. I will now focus on the configuration channel pins. The configuration channel pins are located here on the 5th pin. So here's the CC1 pin and the CC2 pin. So the bottom row is located here. The V-bus is on the 4th pin. So here is V-bus present. And the V-bus is also on the 8th pin present. So the CC1 and the CC2 can be measured on the CC1 pad here, test pad, and the CC2 test pad. The V-bus can be measured on this pad. So this is only for the Nintendo Switch Lite. For the Nintendo Switch and the version 1, version 2 or the OLED version, it's on different locations. So when you plug in your cable into this receptacle, the CC1 pins are used for communication between the devices, so to negotiate the power delivery and other capabilities. So in a good working case, you can see the voltage going up from 5 volt to 15 volt. And if you see that on your amp meter, then you know the negotiation of the power delivery is working okay, because it jumps from 5 volt to 15 volt. After some analysis, I think I know what these test points are. This is the V-bus CC1 line, this ground pin. This is the differential pair data lines for the USB 2.0. Voltage of the battery is located here. So this is the positive side, negative side. This is the temperature sensor. The V-bus here is also present. So these two are the V-bus voltage. It's the ground. Temperature sensor data goes to this test pad. These two testpads are going to a coprocessor. What it exactly does, I don't know, but it goes to the STM32 IC. This goes to the power button. That is the serial data line. So this is the clock signal and this is the data signal. Keep in mind that I reverse engineered these test points, so the meaning of the test point can be different, but I have a good feeling that it's almost correct. So the power delivery data lines 1 and 2 from the USB-C port will go to a power delivery IC, also known as the M92T36 IC. So these lines will go directly to this IC. This IC is called the M92T36, and the configuration pins 1 and 2 will go to pin 37 and 35 of this IC. So the M92T36 IC is present in all the versions of Nintendo Switches. So in the version 1, the version 2, the OLED version, and also in the Nintendo Switch Lite, this IC is always present. So the layout will almost be the same on all those different consoles. This is the backside of the Nintendo Switch Lite mainboard. The configuration channel pins 1 and 2 test pins are located on these two pads. Then we have all those test points in this region. This is ground. These test points here are the test points for the differential data lines for the USB 2.0 data lines. This is the filter, ground, and this test pad here is the V bus. So the V bus comes from the USB-C receptacle or the port. It will go here through this fuse, through this first MOSFET, second MOSFET, and then to the charging IC. The purpose of this MOSFET is to provide over voltage protection. So if there is any abnormal situation on this voltage line, then it can turn this MOSFET off. The second MOSFET can unload the V bus from the load. This is done when the console is turned off. The capacitors on the V bus line are charged, and we want to prevent that the charge voltage goes back into the V bus power rail. To avoid that, this MOSFET is turned off, and the remaining capacitance is being discharged through a discharging circuit. The first and the second MOSFET are controlled by the M92T36 IC, that's a power delivery IC. This pad goes to the APU. This test point goes to the Wi-Fi IC on the front side of the mainboard. And this is the temperature sensor data that comes from the battery. So this sensor data goes to this test pad. It also comes to this test pad, and eventually it will go to this fuel gauge IC. What this IC does, I will explain it in the next few sheets. This is a current sense resistor that belongs to this fuel gauge IC. So how does the communication look like on the CC pins? So the CC1 or the CC2 pin, depending on which channel is configured for communicating with the host. When you plug in the USB cable, the power supply will deliver a default voltage of 5 volt on the V bus. It will send also a message that it can deliver 5 volt at 1 amp, 9 volt at 2 amp, 15 volt at 1 amp. This is just an example. The power delivery controller in the Nintendo Switch will choose one of those options. So let's say it wants 15 volt at 1 amp. It will send a message back to the power supply. The power supply will send a message that it accepted the request. At that point, the power supply will raise the V bus voltage to plus 15 volt. And then it will send a message back to the power delivery controller with power supply is ready. And after the message has been sent, the voltage on the V bus is 15 volt. So as you can see, all this communication that is going on between the controller and the power supply is done on the CC pin. On the Nintendo Switch version 1, 2, the OLED version and the Nintendo Switch Lite, there are some integrated circuits, some ICs or BGAs that are used on all those versions. First we have a charging IC called BQ24193. So this is a charging IC and this will charge the battery. Then we have the power delivery IC, the M92T36. And this is responsible for the power delivery negotiation that we just explained in the previous sheets. Then we have some power management IC that is responsible for generating some voltage power rails. The eMMC, where the firmware is located. Then we have the APU. And here you can see the fuel gauge IC. This is the battery. This is the battery connector. This is a USB-C cable coming from the power supply. And let's say this is the socket on your Nintendo Switch. So this is a fuse. So if there is a short circuit somewhere in this circuit, it can blow this fuse. So in this blue region we have an over voltage protection. We will see later on how this looks like. Then we have a voltage regulator. I suspect it will deliver 5 volt at the VCon in pin. And this 5 volt will be used to send to the USB-C cable on the VCon pin. So if one pin is the communication pin, then the other one is the VCon pin. And what I think what is going on is that the voltage regulator, the 5 volt, will go to one of those pins and it will go to this IC, if there is an IC in the cable. This is the fuel gauge IC. It will measure the current capacity of this battery. You can see it on your right top corner of your Nintendo Switch. There will be an icon, a battery icon with the percentage of your remaining capacity of the battery. And that is all being calculated by this IC. So how does the charging and power circuit works on the Nintendo Switch? First you have to connect the USB-C cable from the power supply into your USB port. Then the USB port will deliver a default voltage of 5 volt on the V-bus line. The voltage of the V-bus line goes to a voltage regulator. The name of the V-bus becomes VEX or external voltage. That will go to the M92 and also to a voltage regulator to generate this power rail. Then the power supply will start communicating with the M92 IC, the power delivery IC. And the power delivery IC will negotiate which power it wants. So let's say it wants 15 volts at 1 amp. The power supply will deliver 15 volt and 1 amp on the V-bus, also on the external voltage rail, pass the over voltage protection, and eventually it will go to the charging IC. The charging IC will send a voltage on the battery voltage line, the VBAT line, directly to the connector, to the battery connector, to the battery. So the positive pin will go directly to the BQ chip. The VBAT line will also go through the fuel gauge IC to power this IC on. The fuel gauge will also detect if there is a battery connected. It can do that on the middle pin. That's a thermal pin or the A in pin. So if there is no battery connected, the fuel gauge will know that and it will communicate back to the APU. And this communication is done by the I2C communication lines. The APU will communicate to the different ICs. Let's say the BQ, the M92 and also the fuel gauge IC. And your Nintendo Switch will not boot up. The logic to determine what to do when there is no battery connected comes from the eMMC. In the eMMC, the firmware is located and that will determine how this program interacts with the different conditions. This is the current sense resistor, and the current sense negative line and the positive line are directly connected to this fuel gauge IC. With this current sense resistor, it can measure the remaining capacity of this battery. Let's say this battery gets really hot. The fuel gauge IC will notice it on the thermal pin. And if there is a condition that is critical, it can send an alert signal directly to the APU. So when the APU sees this alert signal, it will send commands to all of the ICs that are listening on this line to stop its operation. So this alert line is a interrupt line that will interrupt all processes. The APU also sends an enable signal to the voltage regulator that will turn on to generate the VCON in power rail of 5 volt. So this enabling signal comes from the APU. The APU can also send a reset signal to the M92T36 IC or the power delivery IC, so it can reset this IC. The charging IC, if all conditions are okay and the battery is charging and everything is within the limits, it will send a charge status back to the APU and also a power good signal to the power management IC. So this is the primary power management IC. If it sees that this charging IC is working okay, it will start generating some voltages. Also, this power management IC also communicates through I2C with the APU. If everything is okay, the charging IC will start generating the system voltage of 4.2 volts, and this voltage is always present. So this is the main system voltage. So this is the circuit how it looks like when you have a USB-C cable connected. In this scenario, there is no USB-C power supply cable connected, so the power does not come from the V-bus. So M92 or the power delivery IC will not work. But how does the main system voltage being generated then? Well, that's because we have a battery, and from the battery the power will go on the VBAT line. The fuel gauge IC will also calculate the capacity remaining on this battery, and this voltage on the VBAT line will go to the PQ charging IC, and the PQ charging IC will generate the 4.2 system voltage. In the previous scenario, the voltage comes from the V-bus and the charging IC generates the 4.2 volt from the V-bus. In the case there is no cable connected, the system voltage is being generated from the VBAT. So that's the main difference, the location from where the system voltage is being created. Without the cable, it is generated from the VBAT, the battery voltage, and if there is a cable connected, the system voltage is being generated from the V-bus, the bus voltage. I will now focus on the power delivery IC, the M92T36. For this IC there are no schematics, but there is an alternative schematic. The alternative schematic comes from the M92T30. It's almost the same as the T36. And based on the schematic of this IC, the T30, I reverse engineered it to analyze this power delivery IC. This is a sample circuit of the M92T30. Here are the CC pins. The serial communication is done in this region, so you see the data line and the clock line. And this line goes straight to the APU. This is the USB-C port. So the V-bus goes to these two MOSFETs. The first one limits the inrush current, so the over voltage protection. And the second MOSFET is used to unload the circuit from the V-bus, because there are capacitors on the power line, the VBAT line or the V-bus line, and those capacitors are charged. So when you turn off your Nintendo Switch, you want those capacitors to discharge, but you don't want the voltage going back to the V-bus power line, back into the USB-C cable. This MOSFET will prevent that. Then we have these two MOSFETs, and these MOSFETs act like a switch to control the regulation of the external voltage. Based on this sample circuit, we will analyze these MOSFETs. So on the main board of Nintendo Switch Lite, but also in the version 1 and the version 2, maybe in the OLED also, you see this configuration near the USB-C port. You see here a MOSFET. I think in this package there are two MOSFETs. These are separate MOSFETs, so this is, let's say, MOSFET 1, MOSFET 2. So MOSFET 1 will act as a overvoltage protection, and the second MOSFET is used to unloading the power line from the V-bus line. In the red you can see the test points This test point is a reset line that goes into the power delivery IC. This comes from the APU. So this is the VCon in. This is the 5V power rail generated by, I think, one of this voltage regulator. Here you have TS1 and TS2. Here's a voltage divider, and this voltage divider is used to set a specific configuration in which this charging IC operates. You set some kind of temperature window. The battery voltage you can measure here. It is the serial clock line. This goes to the coprocessor. I think this test point goes to the enable signal of the backlight. This goes to the APU, but not 100% certain. This goes to the controlling this MOSFET 1 and MOSFET 2 is done by gate 1 on this pin and the gate 2 on this pin. This gate is directly connected to the M92 IC, so the power delivery IC. If you look at the power delivery IC on pin 21 and 23, the gate of the MOSFET 1 is controlled here and the gate of the MOSFET 2 is controlled here. Also, we have the V-bus power rail coming from the power supply. It will go eventually to the charging IC, but in this case we're gonna focus on the external voltage. The V-bus will go through this fuse resistor, through this MOSFET, and it will go to the power delivery IC. It will also go to this, I think it is a voltage regulator to deliver some voltage. So this switch controls the external voltage to enter the M92 IC and to also go to this regulator. The controlling will be done in this MOSFET. MOSFET 1 in this package, the gate 1 is controlled here and the gate 2 is controlled over here. If we look at the power delivery IC, we can see the gate 1 of the external voltage MOSFET goes into pin 24 and the gate 2 of MOSFET 2 will go to the pin 26. As you can see, it's also controlled by this power delivery IC. And the external voltage will also enter on pin 28 and it will go to this power delivery IC, the M92. This is the differential pair data lines of the USB 2.0 and this goes directly to the APU. Here you can see the high-speed transmission lanes and I think it doesn't go anywhere because we don't have any HDMI signal in the Nintendo Switch Lite. Data lines coming from here, the transmit and receive lines, goes nowhere. Also this voltage regulator, I don't know exactly which voltage it generates, but the voltage will go to the power management IC, the backlight IC, the LCD driver and the audio IC. So to recap, the V-bus voltage will go to this MOSFET. From here it is a external voltage. This external voltage is controlled by the M92 IC that will control this switching MOSFET, and when it's turned on it will go and deliver it to this M92 IC, but will also be the input of this voltage regulator. If we look at this sample circuit, what we can see is we have a input of a power rail here. So this is 5V. So there's a power rail of 5V going into this power delivery IC. The external voltage that comes from the V-bus goes also in this power delivery IC. Then we have the V-bus. The bus voltage will also go to this IC on this pin. But why does this IC need 3 different voltages? In this image you can see that the plus 5V goes into this pin, the external voltage on this pin and the V-bus on this pin. So V-bus can be up to 20V and the external voltage also goes up to 20V because it's derived from the bus voltage. Then we have 5V voltage coming into this pin, and in the power delivery IC we have a power selector. This power selector selects the lowest power supply that is getting into this IC, so the 5V power rail, the external voltage or the bus voltage. So the internal power supply can be measured on VCC in pin. So on this pin you can see which voltage is being used to supply power to this power delivery IC. And this internal power supply will generate some voltages, 2.8, 1.5 and 1.5 internally. These are low drop voltage regulators. And then we have 3.3 volt on the VDD I/O, and this voltage is used to generate the serial data signals. So this is the M92 T30 pinout. I'm gonna assume that this is the same for the 36. So first pin is the ground pin. The second pin is connected through a resistor and it's connected to the output of the VCC in. So this is pin 5. So here will be the internal power supply. So it can be 5 volt, 10 volt, 15 volts. Depends on what internally this IC has selected as the internal power supply. So this voltage will go to pin 2 through a resistor. Pin 3, you can configure the ID or the address. I think this ID is used for the serial communication. So with some kind of configuration, you can set the address of this IC. At least that is what I suspect. On pin 4 is the input. It is a digital block reset signal. So this reset signal comes from the APU. Pin 5 is the VCC in. This is the voltage that internally is generated by this power delivery IC. On pin 6, the voltage generated here will be used as the input on this power rail. Pin 7 is a discharge pin, and this is used to discharge the bus voltage power rail. So all the capacitors that are connected on this rail will be discharged on this pin. 8 is ground. 9 is the input pin. So on this pin, the VB pin is the bus voltage pin. So from the USB-C port, the voltage will go also on pin 9 of this IC. Pin 10, 11, 12 and 13 are general input-output pins. And I don't think they are being used in the Nintendo Switch because they are pulled down. Pin 14 and 15 are test and debug pins. I don't think it has a purpose in the Nintendo Switch. Pin 16 is a general purpose input-output. 17 is the same. It's a general input-output, but this one goes to the APU, and I don't know what this pin represents. Pin 18 is the VDD I/O. It's an input, so the 3.3 volt will go through this pin, and the VDD I/O is used to generate the serial data. SM data is the serial data line. It will go to the APU. Pin 20 is a serial clock line. On pin 21 is the gate 1 for the overvoltage protection. So pin 23 controls the V-bus discharge MOSFET. It will go to the gate of that MOSFET. Pin 24 controls the external voltage power rail, so the MOSFET that controls the external voltage. Pin 26 also controls the external voltage MOSFET. On pin 28, that will be the input. The external voltage comes from the V-bus voltage. It will go directly into this IC. And this is used for the internal power selection. Pin 31 and 32 is used for the current sense voltage. So this is the negative side, this is the positive side. So these two pins are used for current sensing. Then we have CC1 and CC2 on pin 35 and 37. So these are the configuration channels. One will be used for the communication, the power delivery negotiation, and the other one will become the VCON power rail. On pin 36, the VCON power rail of 5 volt going into this IC, and this IC will output it on one of those CC pins. So now you know what the pins are doing in the M92 IC. So this is the M92 on the Nintendo Switch Lite mainboard. This is pin 1. The meaning of all these pins I already explained in the previous slide, but now you can see the visual representation of all those pins, but it's basically the same as in this image. You can find the V-bus on pin 4, A4, B9 and A9 and B4. That's on this pin and this pin. You can also measure it on this test point. So the bus voltage comes from the power supply through this receptacle to this pin, to this test point, through this fuse, through these two MOSFETs. So the V-bus will go directly into this charging IC on pin 1. and also at this pin. So these two pins is the input of the bus voltage. Pin 1 and pin 24, the bus voltage is coming in. So 5 volt, 50 volt or 9 volt, depends on what the power delivery controller negotiates. Pin 2 is a power selection input. High indicates a USB host and low indicates an adapter source. I don't know exactly what this pin is doing. I cannot explain that one. Then we have a power good pin on pin 3. So the output power good is active low. This signal goes straight to the power management IC, the MAX 77620A. And the pin on this power management IC is called AC OK. If this IC is working okay, this power good will go directly to the primary power management IC on the Nintendo Switch. I don't know what pin 4 is, but pin 5 and 6 is used for the I2C communication with the APU, so this goes straight to the APU. TS1 and TS2 is a thermal sense pins, and these pins are used to program the temperature window. So charge suspends when either the TS pin is out of range. So depending on what is programmed here, it will set some limits for the thermal sensing circuit. Pin 13 and 14 is the VBAT pin. VBus goes into this charging IC. It will send a charging voltage through these pins back to the battery and the fuel gauge IC. When there is no VBus present, the battery voltage will go to this pin and it will go to the sys pin, because the sys pin is the system voltage pin and it derives from the VBus or the VBAT. So 16 and 15 is always powered on, 4.2 volt. 17 and 18 is the ground. Then we have the switch pin on 19 and 20. So this is the output voltage after switching. This goes to a coil, and from the coil it goes here and also to the system or the Nintendo Switch circuit. Then we have the bootstrap. It's a PWM high side drive or positive supply, so I don't exactly know what the purpose is of this one. So 22 is used as a voltage rail. It will deliver voltage to the divider circuit that's located here to program this temperature window. So this is eventually a low drop voltage rail. Then we have PMID. So this is an internal test voltage between the VBus and the PMID pin. There is a MOSFET, and this MOSFET is used to check the internal health of this IC. So basically, the voltage that is present in VBus should be measured also in the PMID pin. And if there is something different, this IC could be faulty. Here is the layout of the BQ charging chip on the Nintendo Switch Lite. This is the power delivery controller, and this is charging IC, the BQ24193. VBus goes into this pin. The switching pin are located here, and the system voltage is present here. So the VBus goes into pin 1 and 24. It will generate the system voltage of 4.2 volt, and the source comes from the VBus or the VBAT. So if there isn't a power supply connected, then VSys will come from the VBAT, the battery voltage. So the battery voltage will go into this IC. It will start generating the system voltage of 4.2 volt. So this resistor divider will set the temperature window. Now you have a basic understanding what the charging IC does. In this sample circuit, you can see that this is the serial connection. So this goes straight to the APU. Then we have the switch pin. And as you can see, when it starts switching, it will go to the system pin of this charging IC. And then you have your battery pins here. So the VBAT is coming here. This is the VBus. You have the boot pin. So on the other side of the boot pin, you see 4.2 volt. And on the other side of this capacitor, you should see 8 volt. And if this capacitor is not working correctly, then you can see that your console is slow charging, and that can be because this capacitor is faulty. So let's say we don't have a power supply connected to the VBus, so the USB cable is disconnected. voltage come from the battery. It will go into this charging IC. It will go to the sys pins output, and it will be delivering the system voltage of 4.2 volt to the system, to the Nintendo Switch Lite. When you have a power supply connected, the voltage V-bus will go into this charging IC on the V-bus pin. This charging IC will start generating the system voltage of 4.2 volt, but it will also charge this battery on the V-bat line, the battery voltage line. Now you know what the power delivery IC is doing in the Nintendo Switch, and also what the charging IC is doing. Next, I am going to analyze the fuel gauge IC. Fuel gauge IC that is used in the Nintendo Switch is the MAX17050. This IC is used to calculate the capacity of the battery, and the capacity can be shown on the right top corner of the Nintendo Switch. So this information here is being calculated by this IC, the MAX17047. This fuel gauge IC gets its power from V-bat, the battery voltage that comes from the battery pack. So it will go into the V-bat pin. Then you have the thermal pin, the middle pin of the battery connector. That will go to the A-in pin and the thermal pin. You have the A-in pin, so the A pin detects the battery insertion or the removal detection. And it also is used for the thermal measurement that comes from the middle pin of the battery connector, so this battery connector. And the thermal pin is the supply for this resistor divider that is located in this region. Then you have a voltage regulator bypass pin. I don't know what this pin does. Then we have the current sense positive pin that is connected to this sense resistor here, and the current sense negative resistor pin, and also connected on this side of this current sense resistor. So this is on the ground line, and this current sense resistor calculates the remaining capacity of the battery. So the A2 and A3 pins are the serial communication pins. This is the serial data pin and the serial clock signal, and as you can see, this goes directly to the APU. So let's say this battery is overheating. The fuel gauge IC will detect it, and it will send, for this example, an alert signal. So this alert signal will go directly to the APU, and the APU will shut down the whole system. So this alert signal is an interrupt signal, which the APU can use to stop the current processes for the Nintendo Switch. So that is why when you don't have a battery connected, the Nintendo Switch Lite won't boot up. Also, if you have some water damage or there's some corrosion in this IC, or this IC is shorted, it will also prevent the console from booting up. The fuel gauge IC is located on the backside of this Nintendo Switch mainboard. It's located near the USB port, and you can recognize it by this IC and this current sense resistor. This line here is the alert signal, and it goes straight to the APU. The battery voltage comes on this pad into this fuel gauge IC. The thermal pin C2, so this thermal pin can be measured here. This fuel gauge IC is used for the Nintendo Switch version 1, 2, the OLED version, and also for this Nintendo Switch Lite. What will happen when you press the power button on your Nintendo Switch? So in this case, as an example, I used the Nintendo Switch Lite. First, the charging IC has to deliver the system voltage of 4.2 volt. This will go to the primary power management IC. The power management IC will generate some voltages. When you press the power button on your Nintendo Switch Lite, this signal goes to the power board or the Joy-Con board. It will go to this connector. From here it will go to the 6th pin from below, and from that the signal goes through a ribbon cable to the main board, and from the main board it will go to this pin 15 of this STM32 coprocessor. This coprocessor is used to process the low speed signals like the volume buttons, sound signals, joystick signals. It first goes to this coprocessor, and this coprocessor will communicate with the APU by a I2C communication line, so the serial data line. So this coprocessor is connected to the APU, and it will communicate with the APU. So when you press the power button, this power on signal will go to the APU, and the APU will generate a enable signal called EN0, enable 0. So this signal will go to the power management IC, an EN enable 0 pin located on this power management IC. When it gets that signal, it will start generating more voltages. So voltages in standby mode, voltages in boot stage 1, boot stage 2, and eventually the power on voltages. So all the voltages will be generated by this power management IC, the MAX77620. When the voltages are being generated and everything's okay, it will send a chip enable signal directly to the secondary power management IC. So there is a pin connected to the power management IC that will go directly to the secondary power management IC. And this secondary power management IC will generate a 0.8 volt. It will start generating the 0.8 volt if there is a chip enable signal, and also if the APU sends a command to this power management IC. Via I2C communication, there is also a signal coming into this IC, also in the primary power management IC. If everything is okay, it will start generating the 0.8 volt. So let's say your eMMC is faulty, so you have corrupted software. The APU will not send an enable signal to this power management IC. Maybe also to this power management IC. Let's say the eMMC is bad. What you will see is that your console is stuck in some kind of current. So let's say 20 milliamps or 45 milliamps, but it doesn't boot. It doesn't go to 7 milliamps and then back up to a higher current. And that's because the APU cannot communicate with the eMMC, and therefore the enable signals are not sent to the power management ICs. Also, the APU communicates with the primary power management IC, the secondary power management IC with the eMMC, with the coprocessor, with the power delivery IC, the fuel gauge IC. So everything has to be okay in order to boot up the console. And this principle is the same for the Nintendo Switch Lite, the version 1 Switch, the version 2 Switch, the OLED version, because they all use the same ICs. In the Nintendo Switch Lite, it uses a coprocessor, but in the Nintendo Switch and Switch version 1 and 2, this signal, this power on signal, is generated on a different way. But eventually it will go to the APU, and the APU has to generate an enable 0 signal to the primary power management IC. And this is how the power on section works. This was the in-depth journey through the charging and power circuit of the Nintendo Switch. I have covered the charging, the power delivery and the fuel gauge circuit, which can give you a better understanding why you need to replace an IC. So if you want to repair a Nintendo Switch with a no power symptom, this can help you identify the problem areas. If you like this type of in-depth analysis and want to see more, then don't forget to give a thumbs up and hit that subscribe button for more in-depth circuit analysis. Thank you for watching. Until next time, bye bye.